So good morning, my name is Pietro Ferraro. I will be the chair of this session of Optical Microsystem Conference. We have the pleasure to have 4 speakers for this session. The first one is an invited talk given by Professor Luciano De Sio from the University of La Sapienza. And the talk will be biomimetic pyramids for plasmonic photothermal therapy. So thank you very much, and sorry for the delay for the technology. Thank you very much.
Okay.
Please, Luciano.
Probabilmente dovrei stare lì io. Probabilmente devo stare qui. Sì, perché...
Ti ho fastidio?
No, assolutamente no. Okay. So I will be sitting here for you. It's okay? Okay. Or I can stand, whatever you want. Okay, I can even stand. Yeah.
If you wish, I can switch the slides.
No, I can do that. I can do it. Okay, so good morning, everyone. I'm so glad to be here. And before I start, special thanks to the organizers for this wonderful opportunity. Today, I will be presenting results concerning the realization of a new generation of gold nanoparticles, keratin-based, very useful for plasmonic photothermal therapy applications. And along the talk, we'll give you new insights concerning other fascinating applications. Okay, this is something I have done with my co-workers at Sapienza University, with Monica Foxan in Romania and Giovanni Perotto at the Italia Institute of Technology. Shortly, the outline of this presentation is a few words about the photothermal properties of plasmonic nanoparticles, how smart materials like liquid crystals and hydrogel can be utilized for detecting the temperature change nearby the particles. And then I will be presenting this truly innovative generation of bio-inspired biomimetic gold nanoparticles and how they can be utilized for plasmonic photothermal applications. And lastly, we'll give you an insight about the possibility to utilize also the photothermal effect of gold nanoparticles against COVID-19 by producing a truly interesting smart face mask. And of course, I will go all the way down to the conclusions. Nanotechnology is a wide-spreading word dealing with the realization of a characterization of very tiny objects. Today, nanotechnology is utilized in several research fields, ranging from medicine to optics. Nanomaterials and nanoparticles play a very important role in the nanotechnology field, not only because they have peculiar optical and geometrical properties, but also because you can connect them all together for making material with unique and fascinating properties like the so-called metamaterials. As you are aware of, there are several kinds of nanoparticles, but for today, I will concentrate the attention of gold nanoparticles. Gold nanoparticles, also named plasmonic nanoparticles, have the unique capability to squeeze down a huge electromagnetic field at the nanoscale thanks to a physical phenomenon which is called localized plasmonic resonance. In other words, you shine on a visible or near-infrared electromagnetic radiation, this will produce an oscillation of the bulk free electrons, and such a coherent and dipolar oscillation is called localized plasmonic resonance. As a matter of fact, you can change the frequency, the intrinsic coloration of gold nanoparticles by playing with several parameters, such as size, shape, and geometry, and so on. But remarkably, there is a very nice parameter, which is the dielectric function of the surrounding medium, namely the refractive index. You change locally the refractive index, and this will change the coloration of gold nanoparticles. You do so, you can control very easily the coloration, the plasmonic band of gold nanoparticles by acting on the surrounding medium. Associated to these very intrinsic optical properties of gold nanoparticles, there is a strong temperature increase nearby the particle due to the absorption, essentially. If you take a look to the temperature profile, the temperature is uniform throughout the particle, but as soon as you go a bit far away from the particle, there is a kind of exponential decay. It means that the temperature increase is localized exactly nearby the particle surface. You do this, you have the capability to squeeze down now the temperature increase at the nanoscale. So then opening new opportunities for several applications. And of course, the temperature increase is proportional to the intensity of the instant radiation. It is very important to monitor, to detect, to measure the temperature increase nearby the particles. We did start working on the subject, I should say now 10 years ago, when we first combined the unique property of smart materials like liquid crystals and golden nanoparticles. In other words, by using the thermosensitivity of liquid crystals, we were able to demonstrate the capability to measure with very high precision the temperature increase nearby the particle under a suitable laser excitation. In the first experiment, I'm just showing the combination of cholesteric liquid crystals. Those liquid crystals are like springs essentially, and golden nanorods. When you activate those golden nanoparticles, you can do two things. You can measure first off the temperature increase nearby the particles. You can change the elongation of cholesteric liquid crystal, thus making a kind of tunable Bragg mirror. Another compelling application was a bit different in a kind of layer by layer geometry, where we cover spherical golden nanoparticles again one more time with cholesteric liquid crystals. And a few years ago, we demonstrated a new generation of switchable diffraction gratings by combining holographic diffraction gratings and golden nanoparticles. And of course, if you are interested on these topics here, you can take a look to these few papers that they summarize very well all the efforts we've done in the past 10 years. Moving forward with the devotion to make bio-related applications, we decided still to work with thermosensitive materials, but with less complexity and essentially water-based. We combined golden nanoparticles and hydrogels. Those are thermosensitive materials, and very easily you can see that the material is water-like at room temperature, but you heat up close to the body temperature, the material turns out to be cloudy, like milk. By triggering this phase transition with golden nanoparticles, we were able to demonstrate a smart windows where can be activated by using a low-power white light. So this is the main application we are working with. And again, this was a kind of learning experience for us to control now the temperature increase in water, which is, as you are aware of, an excellent material to start with bio-related applications. So what I was saying is this: we started doing application in optics, and we were saying, what about if now we share this experience, this know-how with bio-related applications? And thanks to the position I got in a medical department here at the Sapienza University, we're trying to combine this experience for cancer-related applications. Now, the point is this: why you have to use golden nanoparticles for cancer-related applications? Okay, let's see what are the main issues. First off, the very high photothermal efficiency. In other words, golden nanoparticles have an extraordinary high photothermal efficiency. For elongated particles, typically the conversion efficiency is almost 1. It means 100%. Moreover, golden nanoparticles are biocompatible, are stable, and very importantly, very easily, you can functionalize the surface. You can put whatever you want, drugs, antibodies, whatever you're looking for, easily you can stick on the golden nanoparticle surface, and they are small enough to fly through the circulatory system. So with this in mind, we had a big issue in the very beginning, which is related to the capping agent utilized for stabilizing golden nanoparticles. If you are familiar with chemistry, once you run the process for synthesized golden nanoparticles, it's mandatory in order to have a stable colloidal solution like this, having surface functionalization. This will avoid aggregation between particles, thus producing colloidal, the so-called colloidal stability. And typically, the material we utilize for stabilizing, it's a very bad material with very high toxicity. This is well-known CTAB as an example. That's why you have the beauty of those materials, but you cannot work with because the toxicity is very high. So then we said, so what about if we would try to change this coating here with a bio-inspired materials? We tried several materials, several proteins, and we ended up using keratin. So keratin is a wonderful material. It's a bio-related, of course, material. It's very stable. You can work with, you can dissolve in water, and you can post-functionalize very easily. So then we said, what about if we make those particles coated with keratin? So we tried. I should say that we did a great job for achieving this result. And I want to give you just an insight about this capability to make keratin coated golden nanoparticles. First off, you can see the difference in terms of spectral response. Once you connect the keratin here, there is this shift of the plasma band, then highlighting that there is a change locally in the refractive index, because now we go from citrate, like the pristine particles we have, and they're coated with keratin. So then since we change locally the refractive index, there is this shift. Moreover, you can see here, this might be, it's not very evident here, maybe here is even better. You can see this very tiny organic layer surrounding the nanoparticles, then confirming the presence of keratin. And lastly, of course, there is a strong change in the zeta potential. So once we were sure, even with other techniques, that we have stable keratin-coated golden nanoparticles, we decide to check now the viability of those particles. And as a comparison, we have here CTAB-capped golden nanoparticles and also citrate-capped golden nanoparticles, like the one you can buy very easily. So to give you an idea, the red curve is the viability in presence of golden nanoparticles with CTAB. And you can see that after 24 hours, due to the very high toxicity, you can easily kill the cells. And this is something bad, because we don't want to kill the cell with the toxicity of the material. We want to kill with external perturbation like light. So conversely, you can see that our particle, which is the blue curve, the viability is very high, 100%, I should say, even after 72 hours of incubation. And as a comparison, here you have this citrate-capped golden nanoparticles. Of course, they are very high biocompatible, but we cannot work with that because the stability is very low. Those particles are not very useful for real application. That's why the comparison is between our particles and the CTAB-capped golden nanoparticles, and you can see that there is no comparison. To begin with, we decided to work with a very aggressive form of cancer, which is this glioblastoma. This is a brain cancer. That's why we decided to work with something which is very challenging right now. In order to understand where particles are, we decided to make a fluorescent tag here on golden nanoparticles. And of course, here you have the control. You can see very well the nucleus of the cell and the cytoskeleton, which is this reddish part, and of course the margins. When we have the cells with golden nanoparticles, you can start seeing these green spots. Then they colocalize very well on the nucleus. That it means that we have a lot of particles nearby the cancer cells. And just to give you an idea, those images were acquired once we washed the cells. So in other words, we are mimicking the flow of golden nanoparticles through the bloodstream. So it means that those particles are either stuck on the cell surface or maybe have been internalized. So something else we did, we tried the number of cells positive to golden nanoparticles, to keratin. And you can see that after 48 hours, 70% of cells are loaded with keratin-based golden nanoparticles. And in order to understand where particles are, we did perform ultrastructural localization with a quite high resolution TEM. And you can see that particles are very well internalized by the cells, and we have even particles in the endosome, these very small vesicles, which are here nearby the particles. And of course, we have also particles outside the membrane. It means that very easily they can be internalized, and easily we can uptake those particles, those cells with our golden nanoparticles. And I should say that right now we don't have any specific functionalization for for targeting. This is something we are addressing. I will give you more details a little bit later on. So something else we did once we were sure about the beauty of our particles was to test in operational mode. So what we do, we have ourselves here in the solution with, of course, gold nanoparticles. We shine on a suitable light source, which is a green laser. Green laser because spherical particles, as you saw in the very beginning, the absorption is in the green part of the spectral range. You can see here, what we do is this. We shine on this green laser and we acquire with a thermal camera the side view to measure, to detect the temperature change due to the beauty of gold nanoparticles to convert this external light to heating. As a result, you can see that, of course, we run also the control experiment, means cells without gold nanoparticles. You can see that without nanoparticles, there is no temperature increase. Conversely, in presence of gold nanoparticles, the temperature increase is about 6-7 degrees C. Now, you can say, okay, 6-7 degrees is not a lot. Don't forget that we run our experiments starting from room temperature. Real application, we don't start from room temperature. We start from 37 degrees C, which is the body temperature. So then 6-7 degrees is more than enough for killing cells. That's why we are happy about delta T. We don't care about the temperature we're able to reach. But still, the reduction is not very high. It's about 30%. It's not a lot. That's why. So this kind of cancer cells are very hard. They cannot die very easily. That's why most likely we have increased a little bit the temperature. But here there is a limitation due to the fact that spherical gold nanoparticles do not perform very well in terms of photothermal efficiency. For this, we are looking for something better, for something a little bit more exotic, maybe. And there is another issue. We are working with a green light where the absorption of the tissue is very high. There is no penetration with green. Much better if we can work with a near-infrared laser, the so-called water window, where the transparency in the tissue is very high. You can see here this simple photos. Blue light cannot go through. The same for green light, but reddish light can very easily propagate to the screen. You can do this with your smartphone. You have a torch, you just shine on your finger and you will see the reddish. It means that this wavelength, the longer wavelength, can penetrate through. So then we said, okay, we need particles with better photothermal efficiency and maybe with absorption, the near infrared. For this, we started this amazing collaboration with this group in Romania, with Monica Foxan, and they are able to make very nice and exotic nanoparticles. And the shape is a bipyramid here. You can see very well. This bipyramidal shape tells you that starting from spherical gold nanoparticles, you can grow them for making this kind of elongated shape. These materials are amazing, first off for sensing applications, and also the photothermal properties are terrific from this standpoint. We did characterize a bit those particles, just to give you an idea. First off, the absorption is exactly the so-called water window, so that we are happy for that. Of course, the long diameter is about more than 100 nanometers. It's something still we are trying to work with, but it's still we are in the so-called nano range. And lastly, of course, we have a positive surface chemistry. But in order to run this synthesis, they are forced. They are required to work with CTAP. They cannot use another material. So this is now the ending point of the story. And we said, okay, what about if we try to overcome this issue, if we can do a keratin coating? We tried, and you can see here very well that we succeeded with coating those particles with keratin again, and you can see also the shift of the plasma band, thus highlighting the strong sensitivity of those particles. And once we had those particles keratin coated, immediately we went to the lab to see if the biocompatibility is very high now. And we weren't really happy, because you can see that if you increase the concentration above 25 micromolar, there is a toxicity of those particles, because most likely there is a lot of residual CTAB, and our layer is not enough to coat those particles. Although the photothermal properties are amazing, and we are happy with that, they work with the near-infrared laser. Also, the temperature increase can be up to 30 degrees C. but there is this big limitation. We cannot increase the temperature too much. At this concentration, the temperature increase is about, let's say, 12 degrees C before washing. After washing, of course, this will be much lower. So then we said, okay, we are not really happy. What about if we try to increase the coating of this layer? So then we went through a double functionalization. This is just to give you an idea about the single layer, of course. Once you wash, let's say, the particles, we have very few particles in the cell, the temperature increases 4 degrees C. So then we said, what about if we try to double the layer, to make thicker? And of course, we did succeed. Now the biocompatibility is extremely high, even after 72 hours of incubation, and we can run concentration up to 100 micromolar. So then we have in our hands this very beautiful golden nanoparticles with excellent photothermal ability, and we are running now new experiments, also in vivo experiment, because this is our end goal. So then we'll try to provide an update as soon as we can. But something I want to share with you before I will jump to the conclusion is something else. So this is a kind of loop. We started with optics. So now we are working a lot with cancer therapy and also other amazing stuff. And we said, what about this COVID-19? Can we do something? Can we address, can we help the community? This was the question for us. So then we decided to make an amazing face mask, where by utilizing gold nanoparticles with exotic shapes like nanorods and even bipyramids, we are able now to deposit those particles on the face mask. Once you trigger near-infrared light, you can jump, you can rise up the temperature up to 75 degrees C, and this is more than enough to kill, to suppress viruses. That's why this is a starting point. Something else. Can we increase now the filtration efficiency of those masks? Maybe 100%. So what we did was this. We were electrospinning fibers on top of conventional masks so that we can increase a lot the filtration. I should say that this is a kind of visionary project. And for this, we did publish this very recent work where we try to imagine the next generation mask, where we combine the so-called artificial intelligence for designing, for personalizing the face mask so that we can increase the comfort. We have exotic nanomaterials like gold nanoparticles and also copper nanoclusters, so that we can also, from a chemical point of view, we can sterilize the mask. And of course, there is this capability on demand, might be by using the smartphone. You can very easily sterilize your face mask by using a smartphone. So this is something we're working. It's an amazing project. I truly suggest you to give just a very quick look to this paper if you want to understand a little bit more. Okay, just to summarize, so what we are doing, we are pushing a lot with these exotic golden nanoparticles. And one of the issues we are experiencing when we start in vivo application is the detection. How we can detect where particles are when we inject through in vivo application. So to address this now with amazing results, hopefully I will tell you next time, concerning the possibility to combine with radio tracer, radiopharmaceutical drugs, and gold nanoparticles. It means you can use nuclear medicine for visualizing, for testing with particles once they are injected. And once you localize those particles with this very high quality imaging techniques, you can shine on a suitable light source and you can do the rest. We are also trying to mimicking a little bit the in vivo system without starting, of course, in vivo experiments, by using this 3D bioprinting technique, which is very powerful. And like I said in the very beginning, we are starting with vivo experiments because our wish is to test those particles in vivo to see if they really work in operational mode. I want to thank the financial agencies like the URD. They have been supporting us a lot in the past 10 years or so. I should thank Sapienza University for supporting us through these Ateneo projects, they are called, and also Lazio Regions, who is supporting us a lot, who is promoting our research, they are trying to do their best to support us from this standpoint. And of course, lastly, I want to thank you all for the attention.
Thank you very much, Luciano, for this very interesting talk.
You.
Which you gave an overview of this evolution and application on particle different. Some questions, comments?
Yes, please.
Yes, thank you for the talk. I was wondering, are these nanoparticles is pyramid stable in cell culture media with the same with everything?
Yeah, we tried first with buffers to see if they're stable. With buffers, they're stable, and we tried with different media. And this is the beauty. In this paper, here is out. Actually, in the supplementary information, because one of the reviewers was asked it. Take a look here. The same behavior. Yeah, who is affecting the stability is the keratin coating. That's it. It's not about the shape, because it's in some way increasing the, let's say, the repulsion between particles. They are fully stable, believe me. Here, there are results on spherical particles. We did run the same experiment with these particles here, and they are stable. They are very beautiful. Yeah.
And the other one, now that the people
Yeah.
experiment, are you also going to target the virus?
Yeah, we want to do this first. We want to use radiopharmaceutical drugs because those have the capability to localize in the tumor. So then we will use this for targeting, like FDG as an example, and for imaging. So then we try to have two effects by using one functionalization. But something else we are doing, we are functionalizing for another project with specific antibodies so that they can recognize a marker which is overexpressed in a particular cell. But for this experiment, we're on the very beginning. What we're doing is we just implant the tumor and we just deliver the particle through, let's say, the skin so that we test what is the capability and so on. And then we want to run this kind of experiment. But like you said, we need functionalization. That's it.
No, and also because maybe I don't know, but the glioblastoma maybe 100 nanometers.
I know it's quite big. Yeah, it's quite big. Yeah. Yeah, it's quite big. Big, but just to give you an idea, the particles are used for these more modern vaccines are with the same size. So then this is the typical size when you work with real drugs for nano delivery, let's say. Yeah.
Please. Quick question. Please.
About the mass coverage with the wire, how do this coverage affect them?
Yeah, this is something you are is totally true. That's why we are working with hydrogels, because from this standpoint they are wonderful. And right now we are modifying a commercial available mask, but the idea to use our material for printing the mask. And also with the humidity, which is a big point, we have in mind a way to remove the accumulation of water inside the mask, which is a source of discomfort right now. Yeah, even for the, of course, for the glass, no? Yes. Of course, yeah. This is something you have in mind. And still, there is a very nice approach in this paper I was mentioning, where we describe this possibility. Like I said, it's a kind of visionary paper where we try to see the future in maybe in the next 5-10 years with this truly innovative face mask. Okay, I'm running late.
The last one,
yeah.
Because we are actually something.
Also to use other metals than gold.
Yeah, we love silver. We love silver here. We are working with silver. Yeah, and copper, of course. Like I was mentioning, copper. Yeah, nanocluster. They are beautiful, amazing. Yeah.
I apologize, but we have no time.
Okay,
because we
sorry.
are accumulated some time.
Yes.
So please contact the author directly to go further question. So let's thank again Luciano De Chiro.